Basics of circuit complexity. Okay, so in circuit complexity, the main objects of study are Boolean functions and Boolean circuits. A Boolean function is a function f from the hypercube 0, 1 to the n, so the set of n-bit strings, to 0, 1. A running example will be the n-bit parity function denoted XOR sub n. So on a string x, the parity function outputs the number of ones in x mod 2. In other words, the sum of the coordinates x1 to xn mod 2. So the model of computation that we study for computing Boolean functions are Boolean circuits. So you see here a circuit depicted on the right. Circuit is comprised of and, or, and not gates, and the inputs are just the coordinates of the string. So the way we would formally define a Boolean circuit is as follows. So as a finite acyclic directed graph in which each input is labeled by a variable, each gate is either not and, or. Let me start over because this sucks. Basics of circuit complexity. So the central objects of study in circuit complexity are Boolean functions and Boolean circuits. A Boolean function is a function from the hypercube, so the set of n-bit strings, to 0, 1. And a running example in this lecture will be the n-bit parity function, denoted XOR sub n. This maps a string x to the parity of the number of ones in x, so the sum of coordinates x1 to xn modulo 2. So Boolean circuits are the model we study for computing Boolean functions. The way we formally define a Boolean circuit is as follows. So it's a finite acyclic directed graph whose inputs are labeled by the coordinates of the input string. And each gate in the circuit is either a NOT gate with in degree 1 or an AND or an OR gate with in degree 2. And there's a unique output gate at the top, which is producing the function that the circuit computes. So a circuit with n input variables computes a Boolean function of n variables in the natural way. And the two parameters we'll consider of Boolean circuits are the size and depth. So size we measure by the number of gates, and the depth is the maximum number of gates on an input to output path. So for example, this circuit here has depth 5. And just as a note, sometimes we measure size and depth only in terms of and or gates. So sometimes it's convenient to ignore not gates. In other words, let them count for free. Okay, so this is the Boolean circuits computing Boolean functions. Let's look at some examples. So let's start with the 2-bit parity function. In other words, the exclusive OR function on 2 bits. We can compute this as follows. So this circuit says either x1 is 0 and x2 is 1, or x1 is 1 and x2 is 0. So this is clearly computing the exclusive OR of x1 and x2. Let's say we wanted to build the 4-bit parity function. Well, then we could make a separate copy of this circuit over x3 and x4, and then another copy on top, taking these two XORs as inputs. And in this way, we get a circuit computing the 4-bit parity function. Okay, we can generalize this construction to any n, and we get circuits computing parity of size order n, and depth would be order log n if you build these circuits up in a balanced way. And in fact, you can check for yourself that in total, you'll get 3n minus 3 and an OR gates, and depth 2 log n plus order 1. And it turns out you can show that both bounds are tight. And we'll actually discuss this later on. Okay, so and or not. So it turns out you can compute any Boolean function with just these 3 gates. And so we say that the set and or not is a universal basis. So the term basis refers to the set of functions that are available as gates in a circuit. As an exercise, you can convince yourself that even if we just have and not gates, so if we don't have or gates, then still we can compute all Boolean functions. This is essentially follows from De Morgan's law that expresses or in terms of and not. Even if we just have a single binary NAND gate computing the not and function on 2 variables, that by itself is a universal basis. 2 non-examples are just the set of and or gates. So if I don't allow you negations, that's known as the monotone basis. And just a single binary XOR gate is also not a universal basis. And it's a good exercise, perhaps if you haven't seen this before, to characterize the classes of Boolean functions that are computable by circuits in these bases. Okay, so Boolean circuits give us a way of measuring the complexity of Boolean functions. Okay, we could measure this by size or depth, but here's the definition of the circuit size of Boolean function. This just refers to the minimum size of any Boolean circuit that computes that function. And this is up to a constant factor. This notion of circuit size is sort of independent of the choice of a finite universal basis. So the observation is that for any finite universal basis B, so set of possible gates, the B circuit size of F is within a constant factor of its Boolean circuit size. And to see this, you would simply replace each gate of the basis B with an equivalent constant size Boolean subcircuit. Okay, so let's make a quantitative version of this claim that every Boolean function is computable by a Boolean circuit. So in fact, we'll show that an n variable Boolean function is computable by a circuit of size at most order 2 to the n. Okay, so let's see how we can show this. So it's going to be a proof by induction on n. So consider the 2 n-1 variable Boolean functions, f0 and f1, where f sub b is obtained by substituting the constant b for the variable xn. And we're going to define a circuit C sub f computing f as follows. So assume we have circuits CF0 and CF1. Then C of f will be the circuit as follows. We're saying either xn is 1 and CF1 is 1, or not xn. So xn is 0 and CF0 is 1. Okay, so if you just think for a moment, you see that this circuit indeed defines the function, computes the function f. And clearly the number of gates in the circuit C sub f is, well, we have the gates from CF1, we have the gates coming from the subcircuit CF0, and then in addition we have 4 extra gates, this or, and not. Okay, and then by induction, it follows that the number of gates in C of f will actually equal this number here, which is order 2 to the n. Okay, so this is one way of showing that every Boolean function has at most exponential circuit size. And this actually a stronger upper bound is known. It was shown by Lupinov, I believe, in 1958, that you can actually construct circuits of size order 2 to the n divided by n, so slightly smaller, and that's by a more clever construction. And that turns out to be tight. Okay, so we're next going to see one of the earliest results in circuit complexity, proved by Claude Shannon in 1949. Okay, so uh, almost all Boolean functions, and for concreteness, let's just say more than 99% of Boolean functions on n variables require exponential circuit size. In particular, have circuit size at least omega of 2 to the n over n. And the proof is very simple. It really is, it's just a counting argument. So on the one hand, there are 2 to the 2 to the n distinct Boolean functions. And to see this, note that there are 2 to the n points in the Hamming cube. And to specify a Boolean function, for each of those points in the hypercube, you're assigning it 0 or 1. So there are exactly 2 to the 2 to the n distinct Boolean functions. But on the other hand, I claim that there are at most this number, s plus n to the order s, inequivalent circuits of any size s. So here we're really counting the number of distinct Boolean functions that are computable by size s. And it's an easy exercise to show that you can bound this by essentially s to the 2s. Okay. And the reason for 2 here is because for each AND or OR gate, it has wires to 2 different subcircuits. Okay, so won't give the details of that argument, but once we have this claim in hand, then the theorem follows immediately. It follows that to compute even 1% of all Boolean functions, well, then we require that the number of inequivalent circuits of the given size is at least 1% of 2 to the 2 to the n. So we would need this inequality, but this means that the size s has to be omega of 2 to the n over n. All right, so that's very simple proof, which establishes that almost all Boolean functions have exponential circuit size. Okay, next we're going to define a complexity class associated with circuits. So this is known as P/poly. Okay, so it's going to be this is the circuit or so-called non-uniform version of P, as I'll explain. So so far in this online lecture series, we've been studying the complexity of languages, right? So a language L is just a set of strings of arbitrary lengths. So 0, 1 to the n is 0, 1 star is just notation for string, all strings of zeros and ones. So we can identify a language L with a sequence of Boolean functions, okay? Namely, the nth function in the sequence is just a characteristic function of the language on inputs of length n, right? So fn of x, in other words, equals 1 if x is in the language L and 0 otherwise. And this is a one-to-one correspondence between languages and sequences of Boolean functions. Okay, so this lets us study the complexity of a language in terms of circuits. And here there's an important distinction that we make in complexity theory between uniform and non-uniform models of computation. So far you've encountered already various uniform models of computation. For instance, a single Turing machine, which decides membership in a language L for inputs of arbitrary length. So for any Turing machine, you can run that Turing machine on inputs of any length. Similarly, a deterministic finite automaton would be another example of a uniform model of computation. Non-uniform refers to having a sequence of models, circuits, say, one for each input length. So to compute a language L non-uniformly, we have just a sequence of circuits where Cn is deciding membership in the language, but only can be run on inputs of length n. So when we speak about algorithms in the traditional sense, usually we have in mind uniform models of computation. In particular, in a uniform model, in a single Turing machine or algorithm has a finite description that you can write down. So in contrast, an arbitrary sequence of circuits does not necessarily have any finite description. Okay, so we don't make any assumption about how this sequence is being generated. Okay, so let's just recall what we've shown so far about Boolean functions, but in terms of languages. So to recap what we showed earlier, every language L viewed as a sequence of Boolean functions is decidable by some sequence of exponential size circuits. And then we showed Shannon's theorem that almost all languages, on the other hand, in fact, require exponential circuit size. So this leads us to the definition of the class P/poly. So this is the class of languages that are decidable by polynomial size circuits. Okay, so much less than the worst possible exponential circuit size. Okay, so in other words, languages with efficient circuits. And just to reiterate the point, here we make no assumption about the process that generates these circuits Cn. And in fact, the sequence of circuits can even be uncomputable. Moreover, P/poly, you can easily show, even contains undecidable languages. Okay, you can sort of hardwire an undecidable language into this sequence of circuits. Okay, so now we're going to show that P, so the class of polynomial time decidable languages, is a subclass of P/poly. Okay, so the circuits are actually a more powerful generalization of Turing machines in some sense. And so this follows from the following theorem, that any Turing machine M with running time T of n, so for any function T of n, can be transformed into an equivalent sequence of circuits of size order T of n squared. Okay, so deciding the same language.